Okay, so here we talk about magnets. Actually, in chapter 29, we have some rules, some laws, like the Biot-Savart law and also the Ampere's law to tell you how to calculate how much magnetic field generated by some mechanism, like yes, a current will generate some magnetic field, and in chapter 30 also the changing electric flux will also generate magnetic field. But here we try to go more deep, try to say, oh, is there any unit of the magnet? So actually here, not that deep first, but try to let you know the magnetism of the Earth. Actually, all of us should know we have so on the Earth we have the magnetic field, and usually we will say we have North Pole and South Pole for in the geographic point of view, from the geographic point of view, which means the North Pole and the South Pole. And of course in Macau or in China we are in the northern hemisphere. And actually we have another pole called the geomagnetic North Pole, 10的北极 but actually the geomagnetic North Pole is actually in the southern hemisphere. Yeah, but at least at this moment, actually the geomagnetic North Pole is moving, although not actually so fast, but actually it's moving. And actually this point is not actually the South Pole for the geographical sense. There's some shifting between them, so yeah. But actually this is you can regard the Earth is like a very big magnetic dipole, generate some magnetic field. So maybe in primary school you will know how to use a compass to see which direction is north or south. So I think if it is very near to the geographical North Pole or South Pole, then this will not work. This will not work. It will work as much as you are far away from the North Pole or South Pole. Otherwise, it will be incorrect. And actually, the magnetic field generated by the Earth is very useful. It's very useful. It protects the human being on the Earth actually. So it says Earth is a huge magnetic for points near Earth surface. Its magnetic field can be approximated as a field of a huge bar magnet. Okay, so but that straddle the center of the planet. Yeah, it says it can distort the charged particle from the sun, or actually from the space, which means that suppose we have this magnetic field like this, and let me zoom in a bit. Suppose we have some charged particle, either positive charge or negative charge will work. So if the charged particle is shooting to the Earth in this direction, okay, so in chapter 28 you know the Lorentz force. So this is V, this is V, this is B, this is B. Yeah. So in that case, there will be a Lorentz force V cross B, V point in this direction and B point to this direction. So V cross B pointing out of the page. V cross B pointing out of the page, which means that if the charge is moving in this direction, there will be a force acting out of the page. So it will be something like the charged particle will go in somewhere like this, and yeah, which is shielded by the magnetic field of the Earth. And if it is negative charge, then V cross B still point to the same direction, but yeah, so in that case, the force will be pointing into the page, yeah, something like that. So the charge will be something go in that direction, will not shoot to the Earth. Yeah, so it actually protects the human being, because usually those kind of high energy charged particle is harmful to human being, and just say even though the ultraviolet wave is not good for human being, but yeah, not mentioning the something like the X-ray, the gamma ray, something like that. But actually, there are some weakness of the magnetic field. If the charged particle is shooting from near here, then in that case, the magnetic field will be somehow parallel or anti-parallel to the velocity of the charged particle. The magnetic field here will be somehow pointing this way. So V cross B, you need to multiply the magnitude of the B field and the magnitude of the V field, and also the sine of theta. And this theta is very small, so sine of theta also very small. So it will not diffract the charged particle. So actually, the point near the magnetic north pole or magnetic south pole is the weak point of the Earth. And actually, due to this characteristic, we can see the aurora near the northern European or in the southern American. 这个是极光啊，极光啊，在北欧或者是南美洲可以看到极光。And actually, the aurora is actually the high energy particle shooting to the Earth and ionize the atmosphere. So you can see the aurora. Okay, it also tells you that the field also has some declination, which means that the direction is not actually opposite to the geographical northern pole. Okay, so this is the magnetism of the Earth, and here we talked about some hardcore physics. So I suppose in high school physics you should have learned something like the atomic number, 原子序, and then something like the quantum number, something like that. We should have 4 quantum number, and then you need to something like you know a element like for example oxygen. We should have the atomic number of oxygen should be 8, which means that the electron should be something like 2, 6, and then there are 6 electrons on the outer surface, and then there will be some quantum number for the electrons, something like that. And one of the quantum number is called the spin. You know, the spin can be either positive 1/2 or negative 1/2. So it says it will be something like rotating in one direction, and the other one is rotating in another direction. So it is positive 1/2 or negative 1/2. And actually you don't know why it must be positive 1/2 or negative 1/2. And still I will not I will not tell you how it comes from. Why not it is not 1/3 positive or negative 1/3 or positive or negative 1. Actually it is a solution using the quantum mechanics. You need to solve the Schrödinger's equation, but that's still not enough. You need to also add the relativistic effect to really solve the spin. If you only try to solve the Schrödinger's equation with the hydrogen potential, and you only get the first 3 quantum number. But actually it is already very difficult. You need to use some strange series to get those solutions. So actually that is not possible to cover that here. But actually it tells you that that should be the unit of the dipole, the unit of magnetic dipole, somehow like the charge, because just say we have a large amount of charge, but finally it tells you that the charge is quantized. The elementary of a charge is the electron. So 1e is like 1.6 times 10 to minus 19 coulomb. And here it also tells you that this is something like the unit of the magnetic dipole moment, possibly the smallest magnetic dipole moment you can find in the universe. So it is like this is the dipole moment equals negative e 1.6 times 10 to minus 19. Mass is the mass of the electron, so it should be 9.11 times 10 to minus 31 kilogram. And then this s is another strange value, which is related to this one. So we have here ms is either positive or negative 1/2. H is the Planck constant, 6.63 times 10 to minus 34 joule per joule s over 2 pi. So in chapter 28 I will tell you that actually we will have another notation called the h bar, which is the reduced Planck constant. So it is h bar equals h over 2 pi. So in many of the cases, if you use h bar to write an equation, the equation will be more compact. So for this case, it will be like sz equals ms h bar. So you don't need to divide by 2 pi, something like that. Yeah, so this is s. This is s. And sz is something different with that s, because sc means the spin rotating with respect to the z-axis, but actually it is the overall spin. So yeah, it will tell you that the sc will be quantized. You cannot point to arbitrary angle, but yeah, I don't know what it is, so just let it. You don't know, it is related to the quantum mechanics. I think that's enough. Okay, so if you just plug in this equation into here, then you will get this is called the Bohr magneton. So it is something like the elementary charge, but this one is for the magnetic field. Okay, so Yeah, so if you put an electron in the external B field, then there will be some potential energy. Okay, so which is nothing but nothing different as before. And yeah, so actually this magnetic dipole moment is related to the spin of the electron. Okay, and of course the electron, you cannot separate an electron into even smaller standard particles, so it's not so possible to find a even smaller magnetic dipole here. Okay, one word I can mention is that an electron has an intrinsic angular momentum. Intrinsic. This word is quite philosophical. Intrinsic. 内在 内在. Actually, intrinsic is like it is spinning, but actually you cannot you can actually to see whether it is spinning, because if you have a ball, it is spinning, then you can see there will be some pattern on the ball, then you can see the ball is actually spinning a lot, but actually the electron is too small to observe whether it is spinning, but actually it should be spinning so that it generates something like the magnetic dipole moment. If it is not spinning, then it will not generate the magnetic dipole moment. So we believe that it should be spinning. Another mechanism to generate the magnetic dipole is called the orbital angular momentum. Orbital angular momentum. So you should know that the electron should be rotating around the atom, the nucleus of an atom. So that in that case, it is like if it is an electron rotating around the nucleus, then it is like a current. It's like a current going through a loop. Then in that case, I multiplied by this cross-section area will be the magnetic dipole moment. So in that case, the equation is similar, E over 2m multiplied by L, and L is actually this one. So ml is the quantum number. If you still remember the high school chemistry, then you know ml is from 0, positive or negative 1, up to something like L minus 1, or something like L minus 1. So actually we can also get a similar equation here, but I don't know what it is. Okay, so here we talk about 3 types of magnetism. So the first one is called the diamagnetism. In Chinese, I think it should be yes. It should be 抗磁性 抗磁性. Okay, so this is very interesting. It says a diamagnetic material placed in an external magnetic field B external develop a magnetic dipole moment direct opposite to the B external. If the field is non-uniform, the diamagnetic material is repelled from a region of the greater magnetic field toward a region or lesser field. Okay, so you can see this is this figure. So in the middle, you can see this is a block, and here, which is like which is like a coil, generate magnetic field pointing out of the page, and this fog is actually floating in the air. It's actually floating on the air by the magnetic field, because there are some diamagnetic material inside this fog. So this fog is actually floating due to the external B field. And actually, this one get the L Nobel Prize, 搞笑诺贝尔奖。Okay, so it says the frog is diamagnetic, as is any other animal. So when the frog was placed in the diverging magnetic field near the top end of the vertical carrying solenoid, so every atom in the frog was repelled upward, away from the region of stronger magnetic field at that end of the solenoid. The frog moved upward in the weaker and weaker magnetic field until the upward magnetic force balanced the gravitational force on it, because you can imagine so the solenoid is something like that. So inside this region, the magnetic field is stronger, so outside it will be weaker and weaker. So that frog is placing around here. So of course there will be a gravitational force acting on this frog. So this will be mg gravitational force, and also there will be some magnetic force, electromagnetic force acting on this frog. So as much as this magnetic field is big enough, then these two forces will balance. So you can see, and there it hung in the mid-air. The frog is not in discomfort because every atom is subject to the same forces, and thus there is no force variation within the frog. So it says the force is roughly the same, because the force is not too strong, but yeah, something like the black hole, there will be something like the 潮汐力如果像黑洞的话，就是如果人被黑洞吸进去的话，你头跟脚受到的力就会差很多，那个潮汐力就会把人扯碎，就是有一个字叫做意粉化，就是把人拉成像意粉那样很细很长的那种状态。Okay, but actually not for this case. So it says the frog is still comfort in that case, although it is floating, it cannot move. Okay, and the next one is called the paramagnetism. In Chinese, it's called 顺磁性. Okay, so it is the other way around. So it says a paramagnetic material placed in an external magnetic field, B external, develop a magnetic dipole moment in the direction. So for the previous case, it's called in the opposite direction. So if the field is non-uniform, blah blah blah, so it will attract towards the region of a greater magnetic field from a region of a lesser field. Okay, so this is something like the magnetic field will the external magnetic field will will repel the diamagnetic material, and in this case it will attract the paramagnetic material. Okay, so here, it also mentions some strange things. It tells you that actually the Marie Curie when I was small, we still call her Mrs. Curry, Judy 夫人 but now we start to call her Mary Curry because yeah, it's something like the yeah, no. So actually, Mary Curry tried to find the relationship between the magnetization and the external B field. For the Curry's law, which is like a linear relationship. So you can see here, we have M. M is here. M over M max, which means that this is the maximum value of M. And it is proportional to the B external here. So this is C over T is the slope of this straight line. And so actually for the measurement, if B external is not very large, for example in this region, then it barely match the Curry's law. But actually if B external is large enough, then it will start to distort in this region. Then there will be actually a maximum point here, setting here. But we actually need to consider the quantum theory to get this to get the explanation of this. So actually we will not talk too much about this here. It just says yeah, actually I have not used it anytime, so so just regard it as a sorry here, it's fine. And I suppose I can jump over this sample problem because this is not so relevant to us. And the third type of the magnetism is called the 铁磁性 Theromagnetism. Which is somehow related to us, somehow. 铁磁性. So actually, 铁磁性 Theromagnetism is like, so if you place it in external magnetic field, then it develops a strong magnetic dipole moment in the direction. So it is somehow similar to the paramagnetism, but the difference is that if the field is non-uniform, it still attracts towards the material. And the difference is that there will be something like the hysteresis effect. In Chinese, it is called 磁激效应. So it is somehow like a memory. For the paramagnetism, it is like if you add some external B field, it also generates the B field almost at the same time. And if the external B field disappears, then it will not generate B field anymore. But here, the difference is that, for example, at the beginning, the ferromagnetic material doesn't generate any magnetic field. And if you try to increase the external B field, so this is external. This is the one generated by the ferromagnetism. So it says if you start to increase the external B field to this direction, it will also generate some of the B field in the same direction. But if you go to point B and then you start to decrease the external B field back to 0, it will not go back to here. It will not go back to here. It goes in this direction. So if you totally remove all the external B field, it goes to this point, which means that it still generates some magnetic field pointing in this direction. For example, positive x direction. You need to further generate some magnetic field in the opposite direction to reset, somehow like the reset the ferromagnetic material without generating any magnetic field. So if you further increase the external magnetic field in other direction, it will go to point D here. And if you start to decrease the magnetic field back to 0, it will remain the magnetic field at this point, the same as this direction, just say negative x direction. So you still need to generate some positive magnetic field up to here to really cancel, to reset the ferromagnetic material. So this is something like the memory, because you tell him positive x direction, and then you stop telling him the positive x direction, but he still remember, the last time it is the positive x direction. And if you tell him, this time is a negative x direction, so the next time it will remember, this is negative x direction. So it is related to, actually we are using this phenomenon for the hard disk, Or actually when I was small, we are using floppy. Just say a memes on the internet is like for the office, something like office, or for the Word. The save icon is something like this. Yeah, for the young people, they may think, this is just an icon, but actually this is the storage we will use in, just say 20 years ago. We'll use that thing to store some data. Actually, we will have a 3-inch and a 1/4 to store 1.44 megabyte. Very, very small. And even maybe in 30 years ago, we'll use a 4-inch and this should be 4-inch and a half and 5-inch and a 1/4. So it can be something like 100 or 200 kilobytes, something like that. Yeah. Okay. So actually, we are using the magnetism, the ferromagnetism to store data, which is like, suppose for a hard disk, it can be rotating, and then you try to add some magnetic field in one direction, then you will store a 1 or store a 0. If positive direction is referred to 1 and the negative direction referred to 0, then you can store 1010, something like that on the ferromagnetic material. Yeah. So actually, this is something like the 3 types of magnetic material, and I think this is the end of this